Hey, everybody. Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Today with us, as always, we have Simon, our co-host in Japan. We hear it snowed there recently. Is this correct?
Yep, we're covered in snow as we speak.
All right. Well, you can possibly try to keep up with the snowfall with our guest today, Mr. Eric Gaskell, coming from Montreal, Canada. How's it going today, Eric?
Good. It's good. Felt like -20 here today.
Oh, geez. All right. So yeah, Eric's with a company called Ora Graphene. Graphene has been kind of a buzz in all kinds of different fields of material science over the last couple of years. So yeah, Eric, maybe tell us a bit about the company, but I think kind of important is what is graphene? And what are you guys trying to use it for?
It's a broad question.
Yeah.
Well, graphene fundamentally is a single atomic layer of carbon. So the idea is that graphene has 6 electrons and it creates this hexagonal atomic structure. And if you put it into a single atomic layer, it forms like a honeycomb structure almost. So it's like a honeycomb at the atomic level, which makes it one of the strongest. As you know from engineering, honeycomb structures are used all over the place, but this is fundamentally that structure, and it is one of the strongest, lightest materials known to man. And unfortunately, it's also very difficult to work with, being a single atomic layer thick. And it's difficult to deposit. It's difficult to sustain it, right? You usually have it on a substrate or something to basically be able to handle it. And so what we work with that is actually a slightly different version of the material. It's graphene flakes, so flakes of these single atomic layers of carbon atoms that have been functionalized with oxygen groups. And those oxygen groups basically allow us to sort of cross-link between layers of graphene and make it into a freestanding carbon structure. Yeah.
Okay, so is that a bit of a mix? Is a layman's way to say that? You're using graphene. Would that be similar to like fiber reinforced plastic, but this is graphene reinforced carbon structures?
Not quite, because there are actually carbon reinforced polymers and people using graphene to reinforce polymers. And usually in those cases, you have like between like 2 to 10% of the graphene into a polymer base. But actually what we're doing is about 90 to 98% graphene with a very small amount of chemical crosslinker that basically just allows us to kind of strap between the layers. Yeah.
Okay, is that assisting with like the production yields and things like this? Because I've heard that graphene, it's a very slow process to get it, so it's been hard to industrialize the material into products because you can't make it quick enough. So is that part of the reason for mixing it?
That's exactly the case, yes. Normally for pristine graphene, as people call it, you would need chemical vapor deposition, which is an expensive and time-consuming process. And it's been limiting a lot of the commercialization of graphene. But because we work specifically with graphene oxide, it allows for a much easier deposition process. Ora is fundamentally a materials company first and an audio company second. And so we spend a lot of time working on how we create this material. And so a big part of it is how we can deposit it quickly and efficiently at a relatively low cost.
Okay. And what is it deposited onto?
Well, we deposit it onto molds. So another part of our innovation really is that we can make these membranes into 3D geometric shapes like cones and domes for loudspeakers. And so we create a mold out of a specialized material and then we sort of deposit it onto that shape. And in that process, we come up with these 3D forms of graphene.
I see. Okay, so it's not deposited onto anything. It's
no. In the end, we peel it off, and it's a freestanding.
Yeah.
Yeah.
So the deposition process, if it's not, I think you said the base graphene is CVD, chemical vapor deposition. So what process would you guys use to deposit?
Well, it's somewhat akin to injection molding. So we put it in a liquid base, and then we mold it into the shape with some vacuum and pressure to get it to take the form that we want.
Okay.
So it starts out a liquid, and then we basically extract the base and are left with this the solid shape.
Okay, and then so for the audio category of things, you've been focusing on diaphragms for smaller speakers, or what range of speakers would you be focusing on?
Well, generally with the characteristics of the material, that it's really excels for tweeters and small full range loudspeakers. So we've been working a lot with micro speakers, headphone drivers, and like drivers for smart home loudspeakers, where you have to have a very small, driver deal with a lot of sound emission, which is good for us because, as we build up our capacity to make these membranes, it's nice to start small. There's no reason why we couldn't use it for larger, like 6-inch drivers, but it becomes more expensive with the larger form factors. And we don't have, at the moment, we don't have sort of chambers that are large enough to support much larger than maybe about 6 to 9 inches.
Okay. And so what kind of stage are you at in commercializing the technology then?
Well, we've been sort of taking a very, Silicon Valley startup approach, where we're kind of trying to bring this technology to the major brands first. Rather than kind of trying to bring it up through the supply chain, we've been working, directly with major cell phone companies, audio companies, headphone companies, trying to impress them with the capabilities of this material and try to get them into their consumer devices. And so it's been a long process. We're also continuing to develop the material. There's a lot that can be done with it, and we're seeing improvements, month over month in our ability to improve the stiffness and lower the density. Right now we have the capacity to create about 6,000 headphone membranes a month. I can say that because we needed to do it for our own headphones that we released as a crowdfunding campaign. But we're really looking to scale up our manufacturing capacity so that we can be seriously considered for some of these products that we're talking to these companies about. Okay,
so you kind of find the kind of beta the technology with some experts, and the brand side, they'll always tell you exactly what they want. And so that's kind of I think a very logical way to approach the market. So what benefits are they seeing acoustically from the material? So, lightweight and density are always issues with diaphragm material. And then what does that turn into in terms of what the user hears?
Right. Our big advantage at the moment is our low density. So it's an extremely stiff material, but the low density is where we can really provide a lot of benefits. So oftentimes we're seeing 2 to 4 dB increase in level while maintaining a consistent frequency response to other materials like aluminum or whatever had been used in the original membrane.
Okay. And how does it, well, I guess it's hard to tell without really ramping for mass production, but is there a comparison on cost, like versus aluminum?
Well, cost is a funny equation for us at the moment, and people ask us this all the time, and we have to say, well, it depends on when you place the order and how much the order is for, because we need to increase our capacity. Right now, the people who are doing the depositions, they all have masters and PhDs in material science and chemistry, and obviously that's an expensive undertaking. But we need a really big contract in order to sort of scale up our manufacturing to get to the point where we can bring the production costs down. So we firmly believe that we will get this material to be about on par with an equivalent aluminum membranes. So if you can imagine, aluminum membrane for whatever loudspeaker driver you're using, it shouldn't increase the cost significantly over the aluminum membrane.
Okay.
It's hard to compete with the cost of membranes like paper and PET, but the aluminum the raw material has some value, and the forming costs some money. And we look at what these things cost, and we think we can get there such that we can be competitive with this material that is currently used in consumer products.
Okay, and then so the source of the raw material to develop the graphene from, that's readily available. There's no kind of not going to run into anything like a neodymium issue, are we?
No, it is fairly available. There are several companies making the raw material that we use. So we source from a few different suppliers all around the world. And the cost for the raw material is also going down significantly year over year as these companies ramp up their production and see more demand for these types of products.
Okay, and besides the audio, where might people find graphene in use today?
Well, the use of graphene to reinforce polymers is very popular. You've already seen that a little bit in like tennis rackets or skis, fishing poles, a lot of sporting equipment. It basically allows them to make a polymer, a little bit stiffer, maybe 50% stiffer, while also not increasing the mass very much. So you can make a lighter, stiffer, polymer out of these graphene reinforced materials. There's a lot of work on graphene oxide for water filtration and sieving, and a little bit of work with graphene for thermal conductivity, just to help move heat away from things in industrial cooling applications.
Okay, interesting.
So when you form a diaphragm, is it a stiff material? I mean, rigid material?
It is very rigid. So maybe I'll share a couple slides here to give a bit of context. So I'll jump right to this one where we're sort of comparing the material to other common loudspeaker membrane materials. And the important aspects here are the Young's modulus, which is a measure of the stiffness of the material, the density, which essentially how much it weighs for how much you have, and the loss factor, a damping factor, which kind of describes how quickly the energy will be absorbed by the material. So aluminum, for example, has very poor damping, and oftentimes people refer to like aluminum tweeters as sounding zingy, and that's largely because they retain energy for a long time and it rings out, giving it that kind of zingy sonic signature. So damping can be very important in achieving like a nice smooth frequency response. So our material is currently not as stiff as aluminum in terms of its Young's modulus, but the density is much lower. So when you look at a material, the speed of sound in the material really determines the frequency at which it will begin to break up, right? So for a given dimensional loudspeaker, the wavelength that first fits within that dimension will start to create modes in the membrane itself and irregularities in the frequency response. And the speed of sound is based on the Young's modulus and the density. So the speed of sound in our material is actually currently faster than in aluminum, despite the fact that our material is a little less stiff. And that's because of the much lower density that we have. We're almost half as heavy as aluminum. And so the overall speed of sound is a bit faster. So we look at, how our membranes work in the frequency domain. We're actually getting larger bandwidth than you might from an equivalent aluminum membrane.
And you've got Young's modulus there at 1 kilohertz and at 10 kilohertz. How is that measured? Sort of like a static. It's not a static tensile test, then.
That's right. This is something that happens in polymers a lot, where you have a viscoelastic behavior, where you have a modulus that changes relative to frequency. And for ours, we actually get an increasing Young's modulus with increasing frequency, which is nice because it's, we really need that additional stiffness at high frequency where loudspeaker breakup is likely to occur. So we use a method called TTS, which is time temperature superposition. And basically, we measure the Young's modulus at different temperatures and then use a mapping function to determine how those temperatures relate to different frequencies. And we can then map from the temperature domain to the frequency domain and determine our modulus versus frequency up to, very high frequencies.
Interesting.
Okay.
So when you produce a diaphragm, what's the thickness? So let me put it another way. Like a headphone driver, the mylar diaphragm, the raw material itself is just flexible. It's a very thin film. Is the same? Is it the same for the graphene diaphragms?
No, they're very rigid. So all of our drivers require a suspension in order to allow them to have the excursion necessary to move. So it's more akin to like a carbon fiber aluminum membrane, where then you have a suspension around the outside edge. And they do that in headphone drivers sometimes using, paper. Sometimes they often call it biocellulose to make it sound fancy, but basically paper membranes that are more rigid and not intended to flex. Or even, some are high-end headphones that might use like beryllium as their headphone membrane, and then have a compliant suspension around the outside.
Right. But for other speakers, they always have a flexible surround.
Yes, yeah. We always need a flexible surround for our material.
Mm-hmm.
Yeah. So, for example, this is a picture of our headphone driver, and we use a super rigid, center membrane, and then have a PU material that's supple around the outside edge to allow it to move freely.
Okay.
As long as I'm on this slide, I also may as well point out that this is a electron microscope image of the edge of the material. So if you look at the edge of the material under electron microscope, you can actually see these layers of graphene that are then held together with our cross-linking agents. So, this is a little bit that's flopped up, but you see it's almost translucent because it's so thin. And these layers of carbon are basically stacked on top of each other in a laminate structure that allows us to take advantage of the characteristics of graphene, right? Our material is not as stiff as, a single layer of pristine graphene would be, but we can leverage the very interesting mechanical properties of graphene to create this laminate material that takes advantage of those characteristics.
So
go ahead, Dave.
I was just going to say, so this, just to try to understand it here. So you're using, it's ALD, atomic layer deposition, or whatever that acronym stands for. And so you're layering your graphene oxide to create like a kind of a stack of material. Is that how the structuring works?
Well, the chemical vapor deposition would be one way to achieve that.
Okay.
But what we're doing actually, because it's graphene oxide, allows us to take either smaller flakes. So this wouldn't be a continuous, each one of these layers aren't continuous. But based on the aspect ratio of these flakes, right, they're almost vanishingly thin, but they have some sort of XY dimension, and they want to lay flat. So in the deposition process, they naturally tend to sort of stack and lay flat on top of each other. And then the cross-linking agent then, creates a reaction that holds them in that position.
Okay.
What's the total thickness of a headphone driver membrane?
Well, currently we can deposit between about 10 microns and about 200 microns thick.
Okay, what's a typical
I believe the headphone driver membrane is about 35 microns.
Right. It's very thin.
Yeah.
It is, and it can be a little bit brittle to handle. We have to work with our supply chain to sort of train them to be able to assemble these drivers consistently.
So you'd produce a stack of diaphragms and send them off to a driver manufacturer to assemble?
That's it, exactly. So, we work with a lot of companies in China, and basically we make our membranes in Montreal. We deposit them directly into the shape we want, and then we send them off to partners in China to get the suspension glued and get them assembled into drivers.
Okay. And then is there a plan in place? Like, once you get that customer and you get the kind of market traction, would it be Asia that you would move to for ramping the volume of the diaphragms? Or is it something that you want to? So. Yeah. We're just asking that because is it something that you need to keep close for IP protection?
Well, that is our current strategy. We're keeping it very close. We do it in Montreal, and it has two reasons. One, for IP protection, and two, just because we're continuing to adapt the process to improve it, to try to automate it where we can. And so having the main facility close to home means that we can we can adapt it faster, we can make adjustments quicker. But we definitely see a certain value in having the actual manufacturing happen closer to the supply chains for these types of products. So, we've been considering Asia. We just need, if we had the right partner, I think we would feel comfortable about moving it.
Yeah. Well, we've got our opinions on partnership versus controlling your destiny in Asia. We've seen it a lot with different kind of material science things. And you mentioned in Montreal there, the production in Montreal, and I understand there's a close relationship with McGill in terms of like the talent pool and the some of the ingredients to make this happen have come from the university there.
That's right. My brother and I actually came up with the idea to do this, to apply graphene oxide to the loudspeakers, and really we started with ribbon microphone membranes. We were both at McGill, and studying, and so when we first patented the idea, we had a lot of involvement with the electrical engineering, the chemistry department at McGill. They were very supportive and helped us to, file for the initial core patent and really start developing it for loudspeaker applications. And we're still in contact with them, and they allow us, certain access to some facilities. So, for example, Ora does not own its own electron microscope.
Not yet.
We rely on being able to use one occasionally at McGill to look at what's happening. Yeah.
Okay, and I believe McGill has a pretty good acoustics program, if I'm not mistaken. So was there some kind of fusion between the material science guys and hanging out with some acoustic nerds, or how did it? Or was it? Or
that's kind of it, exactly. I was doing my PhD in the sound recording area, so McGill has world famous sound recording program. There's a lot of well-known engineers go through that master's program, and I did the same. And went on to do a PhD. My brother was actually working with graphene in the electrical engineering department. He was working on a project with General Motors to apply graphene oxide to battery anodes. And, we would get to talking in the evenings about what we were working on, and kind of, drinking beer and hanging out and thinking about what we could, do together. And this idea kind of popped out of that.
Okay.
Yeah.
And so graphene is conductive on its own?
Pristine graphene is very conductive.
Okay.
When you add the oxide layer with our material, it sort of ceases to be particularly conductive. But there are ways that you can restore that conductivity by a process called reduction, where basically you then remove the oxygen again from the formed graphene material. And so there are ways to treat one of our membranes to restore conductivity to a limited extent. We've toyed around with this to help tune the thermal conductivity of the material, but the electrical conductivity is still fairly low.
Okay. Yeah, I was gonna just maybe add Simon's opinion on that. Will the conductivity of the diaphragm affect the electromechanical of the actual transducer? So is that a good thing or a bad thing?
I guess you could come up with a circumstance in which that would be a good thing, but generally the coil or whatever, the electrical aspect of it is totally isolated from the diaphragm.
Right. Okay. Interesting.
So you guys went ahead and built a whole headphone to prove the concept?
We did.
Yeah.
We did a Kickstarter, crowdfunding campaign. It was, sort of a way to, get some attention and also to raise a little bit of money. Actually, it was much more successful than we thought it would be. We were expecting to kind of make 300 pairs of headphones with, some rapid prototyping techniques. And we ended up getting over 3,000 orders.
Wow.
And so we ended up going with, making our own injection molds and kind of going with the full, production in China to get the headphones made.
Was that quite a distraction from the focus of the diaphragm itself, or did you find it to be quite a helpful thing?
Well, if I'm being honest, it's been a little bit of a distraction. Our Ora's goal is not really to be a consumer-facing company. We really want to develop this tech to get it into the hands of other companies and other headphones, and we have had a lot of interest. But this project has forced us to, kind of deal with that consumer side a little bit earlier than maybe we anticipated, and it's been a good acid test. Really, we've had some technical problems with the headphones, but none of them have anything to do with the drivers.
Sure.
We chose the worst possible year to decide to do a small run of manufacturing in China. I think we started our manufacturing run in early March, and then it all came kind of grinding to a halt. So we've been scratching and pulling to try to get the headphones out, but we finally are almost completely delivered with the product.
Wow.
So will it be only people from the crowdfunding that can get their hands on those, or do you plan to do further production runs?
At the moment, only the crowdfunders are the ones that have access. We are considering doing a second run, maybe in partnership with another headphone company. But we're really putting most of our focus into getting the drivers into headphones from other companies.
Okay.
Do you think that headphone drivers is a focus? I mean, headphones is sort of the popular thing.
Well, headphone drivers have proven to be a good opportunity for us because it's a good size for our technology in terms of our ability to manufacture it. The benefits are very clear when people listen to it, and it also has a bit of cachet, like a bit of marketing glitter to it, the graphene aspect. So we've gotten a lot of attention from the headphone space. Also, there's a bit more room in some of these products for a slightly increased BOM cost for some technology like this, right? Whereas a home pod device, those companies are clawing at every penny. So
I would have thought so. So for headphones, sensitivity is not the most critical thing, but for micro speakers, small stuff like that, it's everything is sensitivity. Do you think that's a valid point, or are there other aspects to it?
I think that is one of the most valid points. There's also some considerations about the technology readiness of our material. So, headphones don't have to deal with as severe environmental conditions as maybe a cell phone loudspeaker would, in terms of waterproofness, high temperatures, high humidity. The the targets that some of these companies we're working with for micro speakers that they want us to hit for those require some fundamental research to get there.
Right.
Whereas the headphone driver application, it's a lot more room, more space for heat to dissipate. And generally speaking, people aren't expecting their headphones to be completely waterproof. Other things like that make it a sort of a better opportunity for us.
Mm-hmm.
Okay. So does the sensitivity and the thickness of the membrane, would it be conducive for application in like inside a balanced armature or some kind of like micro, like, you know, those tiny little membranes inside there? Is it, if I understand those structures correctly, is that a feasible?
I actually would love to have the opportunity to try it there. You know, as a very young company, we kind of react to where the market interest pulls up. So we do these engagements with companies and they tell us what they want and we kind of deliver on it. And that's how a lot of our development gets done, is based on just trying to delivering what, you know, specifically somebody has asked for. And we actually did a balanced armature project very early on in our company, and our material really wasn't ready for it yet at that point. But I do wonder, because, you know, balanced armature devices are famous for being very, very resonant. And if it's possible that the higher damping in the graphene material might help with the sound quality of those types of devices. But
yeah.
I hope to someday have an opportunity to try it again in a balanced armature.
Yeah, didn't Simon, we talked to somebody making MEMS mics, and they were playing with or very concerned about the sensitivity of the membrane for the frequencies that they were collecting with the pickup, the mic pickup.
Yeah, well, that's it. When you get down to the very small sizes, mass is it makes an enormous difference, doesn't it?
Yeah. No, yeah, we've spoken to quite a few of these people on this podcast that might have interest in your technology. All right, that's cool.
So as it is, let's say in a micro speaker application, there you talked about waterproofing and there'd be a robustness thing. Does it tend to be quite brittle? Like, would it be if you mashed it, you would fracture it?
Yeah, it can be brittle. It's probably similar to like a beryllium in terms of its robustness. It's usually okay, but if you start poking it, it can shatter, and if you're not handling it properly in assembly, you can break it.
Yep. And then tweeter applications would be an interesting one then. Formed as a dome tweeter.
That seems to be, that's sort of where I thought it would always take off. And for years, actually, I think it was like 3 years before we actually had our first tweeter project come in the door. So again, I assumed this would be like the breakout application would be tweeters, but we've only had a couple opportunities to work on them. But in every case, we've had very good results.
You're not coming through, Dave. I think we might have lost your mic. So.
Oh, sorry. Can you hear me?
There you go. Yeah.
Yeah, I was just saying those beryllium tweeters like Focal use, those are pricey at a bill of materials. I think they're $35 for the beryllium. So you would be competitive and acoustically looked like according to your chart versus that material. So that could be a nice slide-in replacement.
Yeah, that's long been our target, right? There's if we can be the replacement for beryllium at an order of magnitude lower cost, that would make us happy. And we're kind of in there right at the moment. We're kind of a little bit better than aluminum and magnesium, but we're not quite at that beryllium level yet. But our cost is already lower than an equivalent beryllium membrane. So there's some of these companies that do work with these esoteric materials are interested in the graphene as sort of a position in their product line that sits sort of between their diamond technology or beryllium technology and the rest of their product line.
Yeah, so it sounds like the go-to-market strategy should be, just put my opinion here, if I could be so bold, would be to start with some pretty premium, studio monitors or premium headphones, and then kind of as your mass production scalability comes along, filter it out, because you're going to be able to drive the cost out of it, looking at things. So that we can get some market traction with some high end, and then, people will follow.
Yeah, that's absolutely the hope. I mean, we think that we can definitely make this material in the future, we can make it price competitive with other solutions for just everyday consumer devices. But at the moment, we need to start at the high end of these product lines to kind of, legitimize the cost of this early stage technology.
Yeah, because there's you did mention earlier the buzzword in marketing about graphene, and the people just kind of gravitate towards it. I'm not sure exactly why. Where did that come from? Was it like the Nobel Prize, or what made it so cool?
I mean, yeah, it was the most recent cool thing. I mean, I remember, when I was in high school, carbon nanotubes were the thing that were going to change the world. I think that, a lot of people are excited about graphene's potential for its electronics properties, for its ability to maybe, make computers smaller and more powerful, and make transistors essentially out of graphene. So I think a lot of the excitement about it, comes from this idea that it's going to change everybody's everyday lives in so many different ways. And certainly the guys at University of Manchester who first isolated it won the Nobel Prize for doing that. And that brings a lot of attention. So there was a lot, there was very much a rush of graphene research, right around 2010 when they won the Nobel Prize. As with a lot of these things that get a lot of attention early on, the reality of developing the material and finding a good commercial use case for it, and developing in that direction, that all takes time. So some of the excitement of graphene has kind of lulled over the years, but certainly, like when it first happened, when it was first discovered, and people started talking about its potential, there was a lot of giddy interest from even the public.
Yeah, no, I mean, it is a universal theme. The lightweight and strong is in materials. It's everybody's always looking for that magic formula. So yeah.
Could you remind me again what Poissons ratio is?
What's that?
Could you remind us what Poissons ratio is?
Oh boy, I have to preface this by saying that I'm not a material scientist myself,
okay.
But I think it's a tendency for something to stretch and return to its normal position.
Yeah, it's ratio between shear stiffness and tensile stiffness, something like that.
Yeah.
Okay, never mind. Moving on.
Somebody can post in the comments, "Hey, you dummies, don't know what you're talking about."
I'm sure somebody out there knows. One of these ComSol jockeys need to use Poisson's ratio for all their models.
Yeah.
Very cool. So, how big is the company at this point? How many people?
So we're 14 employees at the moment, and we've been growing. We brought in a bunch of new employees, I think, about a year ago, and we're hoping to do another sort of scale up in terms of our size as we move to a new facility. And we're expected to do so in the next few months.
Yeah, I guess growth is kind of a challenging thing in most days, let alone during these COVID times. So yeah.
Yeah, we had a new facility all planned out. We were about to, sign a lease on a new space, and that was we were going to sign in May, and of course with everything that happened, we ended up not taking it, and so we're kind of waiting, holding back to find the right space again, and get the right opportunity to sort of fund that growth.
Okay, and you're obviously a private company still at this point, so that's everything's under your control. That's good. Yeah, all right.
And do you think you'll be pursuing headphone drivers in the short term?
In the short term, yes, I would say that is where we have the highest level of interest at the moment. And particularly from the gaming sector, it seems that a lot of the gaming headphone companies are looking for, innovative differentiators with their competition. So we see a lot of interest there. And I would anticipate something, one of these things happening in the next, year to 2 years.
Okay.
So the high frequency low frequency, fine. The high frequency thing is getting more and more attention. Higher sampling rate, audio signals, audio source material, and so on. And so is that an area that is probably a strength, do you think, for the graphene compared to mylar?
Certainly. I mean, I'll jump ahead here to show a specific example from a headphone driver project that we worked on. So this is a type of project that we often do with companies. We take an existing driver that they have. It's the headphone driver, a micro speaker, or a full range home pod device.
Yep.
And basically we make a new membrane that sits inside that existing frame and magnet assembly and basically works with their whole existing infrastructure. So that it's just a A/B comparison of what happens when we replace their existing membrane with our technology.
You're right.
And so for this, we took a 50 millimeter driver that used a PET membrane and replaced it with our graphene diaphragm. And what we see is pretty remarkable, particularly the frequency domain, because the PET membrane, in order to allow it to move, since the membrane and suspension are the same piece, the whole thing is very soft. And that means you get a lot of modal energy starting at a relatively low frequency. And in these types of polymer membrane headphone drivers, a lot of the times the majority of the high frequencies is kind of almost assembled out of these high density modal resonances that are loudspeaker breakups that are so clustered that they give kind of almost the impression of a smooth high frequency response, but it's actually a lot of clustered peaks and dips. And there's an associated, harmonic and intermodulation distortion that happens with these breakup resonances. With our membrane, it stays rigid up to about 11 kilohertz. The first, harmonic of that 11 kilohertz is above 20 kilohertz. So in the audible domain, we get a very smooth response that doesn't have the same amount of breakup. And you see it in the harmonic distortion down here. The first major breakup mode of this PET membrane is at about just over 3 kilohertz, and then you just have a whole bunch of harmonic breakup frequencies that exist above that, giving it this really significant amount of high frequency distortion. And when you listen to a pair of headphones that uses a graphene driver, it was one of the first things you notice is that lack of distortion in the high end. You might not have realized you were listening to it, but when it goes away, the sound is much less fatiguing, and you can also get much better stereo imaging because you don't have these sort of phase shifting, narrow Q peaks going on.
Okay, that's really interesting.
Yeah, the key word you just said there for gaming is fatiguing. So if somebody's playing whatever for 48 hours straight, they need their headphones not to tire them out. So that's actually a feature that people look for in gaming headphones is ear fatigue. So that's in the acoustic response. Yeah, the brands look for that function.
So and then if you look at the intermodulation distortion, it gets even more stark, the difference between the two drivers. So this is the dotted line is the polymer, and the solid line is the graphene for second and third order intermodulation distortion. So you see in the second order intermodulation distortion, it's much lower than the polymer, and this distortion exists throughout the audible bandwidth. And for the third order, we have almost none relative to the polymer membrane. And that definitely affects your listening. You know, when your brain has to listen through all that distortion, it takes a lot of mental energy. Even if you're not specifically hearing it as distortion, it takes its toll on your attention and your ability to hear detail in the sound.
Wow, that could, just thinking about some of the products people are trying to make for education market. So if there's less kind of distraction in the sound, people are, maybe their cognitive skills are a little bit better. Is that a reality, or am I just dreaming?
I don't know. Unfortunately, listening fatigue is a very difficult thing to measure. You know, I've asked a few of my, psychoacoustics folks that I know, including Poppy Crum over at Dolby Labs, and unfortunately, I've never come up with a really great, metric that one could use, or a technique to use to measure, how much attention / listening fatigue you get from one audio, source versus another. But it's something that's certainly been interesting to me, because I feel it, myself when I listen to, something that's more distorted. When I listen to music off, the cell phone versus off my tannoys or something, it really, it feels like it takes a lot more work.
Yeah, no, it's kind of, I kind of know the struggle is like trying to listen to something that's almost like somebody yelling in your ear at a bar. Like that's like one of my biggest pet peeves is like, I don't care what you're saying. I don't want to hear it. But in a different environment, it might be something that you want to hear. So, I mean, maybe that's a nice analogy.
Yeah. And the funny thing about it is, with you have some of these headphones with all this high end distortion. When you kind of do that A/B switch, when you put on the headphones, the very distorted ones, initially you're like, whoa, this is great. It sounds very bright, very energetic. And then if you just continue listening for 60 seconds or more, then that's when it starts to kind of hit you that it's kind of wearing down your ears, and you're feeling a little bit tired.
Mm.
That's awesome. Is this response like a free field measurement, or is it built into a headphone?
So this is in a IEC baffle
Right.
without the damping paper on the back. So in order to get the bass response, we basically remove all the acoustic damping,
Right.
and then measure it in a baffle.
Very cool. Okay. And there was another one there with stiffness, linearity.
Oh, that's, well, this I can't really take credit for. It's not the graphene that's doing this. It's the fact that we're using a free edge design, right? When you have a single piece where the membrane is the suspension, it's hard to get this linear KMS function over a broad range.
Right.
So often what they do in headphones is then dampen the headphone driver a lot, put it in this pressure chamber so that it doesn't have to move very far in order to produce, bass. But with the free edge design, since it creates a much more symmetric, spring function, and you can
Right.
You can allow it to move further without getting a lot of that low frequency distortion.
Yeah.
And that, when you start looking at this intermodulation distortion, that's why, it's part of why the graphene driver is so much lower, because it's not riding on a lot of this low frequency nonlinearity. That's basically a product of that nonlinear KMS function.
Okay. Yeah, Simon, would you say that'd be a good testing point for those liquid silicon rubber surrounds versus, I think, Eric, you said you're using polyurethane surrounds on these right now?
We use different materials with different drivers, but our current headphone driver uses PU. Yeah.
Okay. Yeah.
I think so. Have you heard of the liquid silicon rubber, guys?
I don't know that I have. It's not the folks that are doing sort of almost formed. They look like mountain ranges, the suspensions there, where it's like peaks and dips and different kind of strange geometries in the suspension itself.
It's
Possibly not. They've just got a technique to injection mold or vacuum form the surround directly onto the material.
yeah, it's injection molded, and they're the guys I know from Taiwan. They're using optical grade tooling, so it's the tooling's the expensive part of it, but the ability to be precise down to 35 microns in the surround, and also design it in 3 dimensions, and then you're bonding the diaphragm dome to the basket ring, whatever the outside part, all in one shot. So you eliminate glue, so it eliminates a little bit of mass. When you're talking about very 40 millimeter down to 6 millimeter drivers, that little bit of mass and the consistency helps out a lot.
That's very interesting. I mean, sometimes we struggle to find the right suspension for this material. There's a lot of interaction between the cone and the suspension. That's very interesting, actually.
Yeah, check that out. Those guys I'm speaking of are early stage as well, so you guys might be able to help each other.
All right. The ultimate driver. What else we got? More graphs.
More graphs. I can show you some more interesting stuff. We have one of the earlier things we did was just a bookshelf loudspeaker. We made one with Misco, company in the US. They also work with Workwin. So they did a lot of early stage sort of categorization of the material and helped us assemble some drivers to kind of test it out. And so our sort of demo speaker that we share at trade shows and sometimes ship around so that people can hear the technology was basically a 3-inch polymer driver, where we did the same process. We took the driver cone, we ripped it out, we made the exact replica in graphene with the same geometry, the same thickness, same everything, and just popped it back in the same speaker. And it's not a particularly good loudspeaker to begin with, but we can see the performance delta is interesting. The first thing you can notice is that the graphene membrane is actually about almost a third of the mass of the original polymer cone. And then even when you add in all the other masses, we still have enough of a mass savings overall that we see almost 2.5 to 3 dB increase in level across the bandwidth relative to that original polymer cone. The other thing we see is that we've extended the bandwidth by almost a full octave because we don't have the speaker breakup at such a low frequency. We push that up to a higher frequency, and so we get almost 3 dB more output and almost a full octave more output.
Fantastic. That's really interesting.
We have a dip in the response here because of the interaction between the suspension and the cone, though.
Yep.
That's a perfect example of us, having some interesting suspension cone interactions.
Yep.
And with this too, we can also kind of look at the benefits of the damping. The PET or whatever the polymer was for that loudspeaker is fairly well damped, at least relative to, say, aluminum. But you can still see in the waterfall plot that the graphene settles much faster in time than the polymer rings out relative to the graphene. And I personally feel that that's a big part of what makes subjectively the sound quality of the graphene material so good.
I guess that is, do you think that's due to the reduced mass, so the damping effect of the acoustic fluid is more pronounced?
Well, it's based on the material itself. The laminate structure and the way that the flakes kind of move against each other creates friction and absorbs energy or dissipates power relatively efficiently. Also, part of the reason why we see this is just because of the reduced amount of modal resonances, right? You can kind of look at the frequency response and see, some of the peak in the response in the polycone is going to ring out. I guess that's about 10K here.
I see. Yes, actually, I read the graph incorrectly. That's the higher frequency is closer to us.
Yeah, that's weird.
Right,
It's a bit strange. This is 5,000 hertz up to 20,000 hertz.
Yep.
Yeah.
Fantastic.
Cool. All right. Yeah. What else can we know?
Well, the other big application for us is micro speakers.
Yeah.
And we've been, trying to, apply this material for microspeaker membranes. And what we see there, our big advantage there is really the mass, the weight savings, and therefore the sensitivity increases that we can see.
Okay.
It's, we're creating membranes that are similar in stiffness to aluminum, but we're able to make it lighter so that you get often a dB or two more output relative to the original driver. So this was a 3209. This is just like an 11 by 9, I think, typical driver that you would find in a cell phone. But the aluminum, you can see the aluminum response down here. All the breakup frequencies are fairly similar, so we're not really, we're not pushing that high frequency limit, which is a lot of companies would like to see us do. They want to see us, really push that stiffness up higher. But we see some potential to get there. But at the moment, what we can offer is this increase in sensitivity. A dB or two more output, depending on the size of the driver and the weight of the voice coil and the other masses that are involved.
And for like mobiles and tablets and notebooks that have like voice control, is the damping characteristic of the diaphragm helping with the voice interactive? Like the voice pickups often can have problems with aluminum, causing a little ring effect and a feedback loop. So does your material help solve that?
Actually, that's a very interesting question. I'd love to know the answer to it. We haven't really gotten that far with our microspeaker applications yet. We're still trying to impress the right people and get it, into some sort of early stage projects.
Yeah. Well, I hear those Amazon sells a couple speakers, so maybe they're a good target if you can solve that problem. Okay.
Indeed.
Yeah, well, that's quite a bit of information on graphene. So Ora Graphene. So yeah, is anything else that you'd like to ask, Simon?
No, I think I've covered everything I've got in mind.
Okay. And Eric, anything else you'd like to add?
No, that's it. I really appreciate the opportunity to come here and talk about what we've been working on. We think it's very exciting. It is again in an early stage, but hopefully we'll start to see it in real products in the not too distant future. Okay, very cool. Yeah, and hopefully 2021 puts us back on the road and we can interact in person. But yeah, thank you so much for taking the time to talk to us today. We really appreciate it. We'll put all the information for your social media connects in the description for everybody to check out. And please ask any questions you guys want to know in follow up to what we've talked about today. And subscribe and like and share this podcast. So thanks, everybody. Thank you, guys.